Hello everybody, today I will talk about our investigation on the mechanical behavior of 3D printed polymer plates. Our research is entitled Mechanical Strength of 3D printed open-hole polymer plates, and this presentation is prepared for the second Mediterranean Conference on the Fracture and Structural Integrity. This research has been performed in the Institute of Product Development at University of Siegen in Germany. This presentation includes introduction, which is a brief overview of 3D printing methods and their applications. Also, a description of fuse deposition modeling technique. I will continue by explaining experimental tests, include specimen preparation, mechanical experiments, and the obtained results. Finally, I will present a conclusion. One of the manufacturing processes which was introduced in the last century is additive manufacturing, and it is known as three-dimensional printing. As a definition, it is process of joining material to produce components from 3D model data. American Society for Testing and Materials and also International Standard Organization classified 3D printing into 7 categories, which are listed here: binder jetting, material extrusion, direct energy deposition, material jetting, sheet lamination, powder bed fusion, and vat photopolymerization. These techniques are suitable for fabrication of different parts, but they have their own benefits and disadvantages. For instance, in different 3D printing methods, multiple materials can be used in one component, which is an advantage compared to other manufacturing processes. Here we have listed some of materials which are currently used in 3D printing techniques. For instance, aluminum, titanium, and nickel-based alloys are used in metal 3D printing. Moreover, PLA, ABS, and nylon are examples of polymer materials utilized in 3D printing. However, there are some limitations in 3D printing. For example, limit in size of the 3D printers and necessity of doing post-processing. Considering advantages of 3D printing, it has been widely used in automotive industry, electronics, aerospace, and medicine. Due to these applications, different engineering aspects have been studied in this field. For example, recycling 3D printing materials, fracture of 3D printed parts, process optimization, and surface treatment are investigated over the years. As already mentioned, material extrusion is one of the main methods of 3D printing. Fuse deposition modeling, or FDM, is based on the material extrusion technology. In this process, a thermoplastic filament is melted in an extruder that continuously moves in the 3D vector space and deposits the material one layer at a time. Here you can see a schematic of the FDM process. Plastics can be generally divided into thermoplastics and thermosetting plastics based on their forming properties. Thermoplastics such as polylactic acid or PLA have been widely used to build 3D printed products for various applications. In this study, we used PLA material to print the specimens. In this table, physical and mechanical properties of utilized material is summarized. In preparation of the specimens, a standard was used and the open-hole plates are printed using FDM technique. For fabrication of the specimen, at the first step, a CAD file was saved as a STL format, and then it was sliced by an appropriate slicing software. Later, the file was used in the 3D printer. In this image, you can see dimensions of the specimen and some FDM process parameters such as air gap, raster direction, and raster width. In this study, the specimens were printed with plus minus 45-degree raster direction, and by the definition, raster direction is a printing direction relative to their loading direction. All other printing parameters such as printing speed, layer thickness, and infill percentage were kept constant. In detail, specimens were printed with the layer thickness of 0.2 mm and total thickness of 4 mm. In this study, a series of tensile tests was carried out under displacement control via constant crosshead movement until failure. Indeed, a hydraulic machine was used to conduct the test under a static loading condition. In this slide, you can see a 3D printed open hole plate specimen under tensile test conditions and fractured specimens in the right side. Regarding to the ASTM standard, failure that occur at the hole are acceptable failure modes. In our study, all specimens showed a failure at the hole, which confirmed their results are acceptable. In this slide, load deflection and stress strain curves of the examined specimens are illustrated. As you can see in the left figure, fracture load decreased with an increase in the hole diameter. Also, the figure in the right side indicated that the slope of the stress strain curve of the specimen is changed with a change in the hole diameter. In this study, we used abacus for finite element simulation of the plates with hole under the tensile load. Here you can see a stress distribution around the hole as a result of simulation. There is a good agreement between experimental results and simulation finding. Experiments showed that the fracture load of the PLA plate with 6 mm hole is around 5000 Newton, and it is reduced to about 3700 Newton for the specimen with 12 mm hole. In fact, these obtained results confirm that the stiffness of the 3D printed open hole plate is decreased with an increase in the hole diameter. Results of the current study indicated crucial role of the hole diameter in mechanical strength of 3D printed open hole plate. As a conclusion, I would like to review this presentation briefly. At first, I briefly describe additive manufacturing and its application. Also, I mentioned some materials which are currently used in this technique. In the second section, details of specimen preparation was presented, and later in the description of the experimental test, detail of the tensile test on 3D printed open hole plate samples are explained. In order to show effect of the hole diameter on the structural integrity of the part, we have illustrated force displacement and stress strain curve of the specimen with different holes. This work as a part of project Smart Production Design Center, SMAP, is funded by the European Regional Development Fund. Thank you for your attention.